current Trust Lab Colloquium. We're very happy to have Akshima here. She doesn't have a last name. And she did her PhD at University of Chicago a few years back. And currently she's a postdoc at NYU Shanghai. And she's been working, and she has a lot of interesting work at places like crypto on hash collisions, time-space trade-offs. Over to you.
Thank you for the introduction, and thank you for hosting me. And thank you for getting to use your talk and online. Today I want to talk about two of my works on finding collisions in hash and time-space trade-offs for that. So I will be talking about two works. The first was a joint work with David Cash, Andrew Drucker, and Hotek Lee. The second was a joint work with Xiao Guo and Jipong Yu. So this will be the talk outline. I will be first presenting some basic definitions. Then I will be defining our model. Then giving an overview of our results. Then I will follow with a high-level comparison of our techniques with prior works, and before I share some interesting open problems in the area. Feel free to stop me and ask if you have any questions. So let's dive right into it. So cryptographic hash function is any function that takes so it's a function that takes input of arbitrary length and output strings that are of fixed length. So this input domain can be infinitely large as well. They are widely used in practically in several security applications. And this is not the only requirement. In order to be used and provide security, there could be some other properties that are required of them. So first I'll give you some applications where they're used. So say password hashing. Here you can see there are like 3 passwords of different length. After you apply the hash, the output is fixed length strings. Okay. So another application is digital signatures. There you can take like files of any size. Generally, how digital signatures work is you hash them, output like a digest of small size, and on that they are encrypted with the sender's private key to obtain the signature, and then those are like sent with the data. That's how digital signatures work. And so irrespective of what the size of this data is, this hash function would have to like output a fixed length string. So the definition I gave initially was that these functions just take inputs of arbitrary length and output fixed length strings, but that is not sufficient. There are more properties required. So say because if that was the only requirement, that's very easy to get. I can define a hash function that just truncates and takes the first 16 bits, just say that. Okay, so I will always get fixed length output. So I could take say all zeros, and then my first 16 0 bits would be the output. And so that's an example of a hash function. And now so this again, there is this example here. We just take a hash and we take the first 16 bits. But this is not a good hash because say you have a digital, so again say you're using it in the digital signature setting, and I hash I will give you 10 rupees, and whatever output, like after hashing it, I will just take the first 16 bits, right? And that's how I define my hash, and I will encrypt it with my private key, and that will be the signature. But realize this. There could be another file where, let's say this, I will give you 1 lakh rupees. That also hashes to the same thing because you're just taking the first 16 bits. So what's happening here is you can easily find a collision in this hash function that I had defined. So that's why that was not a good hash function. That was a bad example of a hash function because there are more properties required, and In this case, I'm showing the property of collision resistance is important for digital signatures. So obviously when these functions map larger input domains to smaller output domains, collisions would exist. There will be two inputs that have the same output. What we need is it should be computationally hard to find these collisions. So say if my output domain is 512 bits, I want that finding collision should require 2 to the 256 order of time. And that 2 to the 256 comes from birthday count. And so, okay. Now, hash functions have been like so far, like how they've been analyzed is, say you have so we think of an adversary that makes T queries, and it's computationally unbounded, hence you can think of it as deterministic. But it's not sufficient to just say that, okay, we have a hash function on which the adversary is making T queries. We need to make some assumption about the hash function, otherwise we can't prove that collision finding is hard. So because of this being like a P versus NP problem, so generally we think of this hash function as a random function. We think of this hash function as a random function, and then we can like prove unconditionally that a random function is collision resistant. So for such a adversary that's making P queries to this random function, we can say, we know that the probability of finding a collision is T square over n when the output domain of the function is n, square bracket n. So when I say square bracket n, that's a set 1 through n. Now, in real world, how would you build these hash functions? One of the most popular construction is this Merkle-Damgård construction, where you have a compression function. So this compression function has a fixed input domain, it has a fixed output domain. You use this compression function to hash inputs of arbitrary length. So say you have an input x, you break it into blocks of fixed size. So if here this compression function, like one of the input domain is like the square bracket m, you break it into that, and then you iteratively apply this compression function on these blocks. And whatever output you get, that is the output, and that is the hash. So this is one of the practical constructions of hash functions. Because otherwise, if you think of like how would you construct a function that takes any arbitrary length input and outputs of fixed length. So we come up with like this was one of the constructions, like it's one of the most popular constructions.
So what is ID?
ID? So here you can just think of it as any like random input, or you can think of it as a fixed input. Depends on the system where you're using or where it's being used. But eventually, in our model, you'll understand why you need this ID. I'll explain that.
Does it stand for something?
Yes, something the initialization vector.
Okay. So output is n bit.
Yes, the output is this n1 through n. So that's the output range.
Login.
So for this Merkle-Damgård, when we analyze this in the random Oracle model that I defined before, here we would think of this compression function as a random function. Now we won't think of this entire thing as a random function, because that is here we know more about from the construction we know how we are using it, right? So how we model it, we would think of this compression function as a random function, and then this adversary gets to make T queries, and it has to output two distinct messages that have the same output under MDH. So, okay, you are querying the little h, which is the compression function, but your output, whatever two messages you output, they have to have collision under MDH. And it has been shown that again the advantage is at most t square over n. So this says that Merkle-Damgård is good enough. That's why because it's achieving the optimal security, right? Even if you thought of the hash function as like perfect and random function, whatever security that was achieving, with Merkle-Damgård construction you can achieve it as well. So it was achieving the optimal security.
So it fits length there's a length extension kind of attacks and
Yes, yeah, we can always do that like padding, and we can like always add the length and yeah. Ignoring that, yes.
What is a random function?
Random function, so in random function you basically say whatever your input is, your output is every output. For every input, the output is uniformly in this, taken from this range. So so the output, like the probability that the output is any I is 1 over n. So it's uniformly distributed over.
But is why x is equal to x is not a
Sorry.
hx is equal to x is not a random function?
Because it's not uniformly distributed. I want hx to be uniformly distributed. For every x, hx is uniformly distributed.
H is random digits.
Achha, h is random number over it. Okay.
H is a random function. So when we say h is a random function, its output on every input is a random value in the range. So like
Understood.
okay.
So in this statement, shouldn't m play some role in this?
No, it only depends on the range, output range. Because so the birthday attack, if you know the birthday attack, so it would like so it basically like, so what is the probability your two, so say you have input A, so say you have like you take like this takes fixed ID, this h takes some x1 and x2. What is the probability h of IV x1 equals to h of IV x2? That is 1 over n, and then you're like doing, there are like t square pairs, so that's how it's t square over n. So it only depends on the output of like the range of the function. So, but here we are assuming that this adversary that we have did not know anything about this function beforehand, this compression. But the thing is, it can learn something about this compression function beforehand and use that to do better, right? And so that's why we study pre-computation. And so what this pre-computation says is there could exist adversaries, and there exist adversaries in real world that take they first try to learn something about the function. They try to make like a lot of queries. They try to learn something about the function, store some of that information in their memory, and then they do again they query the function again, and they try to do better attacks. And this is something that happens even like in algorithms and all. I'm sure you all must have studied. So also like the model that we'll give that also captures non-uniform security. So, and non-uniform security can be important when you're doing like compositions and stuff. So, and one of the examples where this pre-computation has been used is rainbow tables. So rainbow tables are like extensively used in functional inversion, and they're also like this. We have attacks that do pre-computation and do very well.
So for encryption schemes, non-uniform security is a very standard thing, right, from the very beginning. But for hash functions, it wasn't the case.
For
all of them, non-uniform is a more standard version.
Right. Non-uniform has been the more standard version from beginning, right?
Yeah, I think that's why.
yeah, so the thing is like, so for a very long time, we have so there have been attacks that have like for hash functions and all, there have been attacks, but like studying the lower bounds or like the upper bound of the security, that is fairly recent, I would say. Like, so I think it's been started like one of the earliest like we know is 2010.
So maybe also another thing is this idealized model with a random. So what you're thinking of is computational hardness assumptions are made against non-uniform address restrictively. But in the random order model, I think just assuming that from the beginning all you have is access to the random oracle as a more standard.
Okay, so I want to define the model, our model next that we analyzed. So this was first proposed by Akshima in 2007. Here the adversary, so this adversary can work in two stages. In the first stage, it gets unbounded access to the hash function. So when I say unbounded access, you can think of it can look at the entire function table. So it gets unbounded access, but it's bounded to output only S bits of information. So it can look at the entire function table, but it outputs only S bits. And this S bits it sends to the online, its online adversary, like online phase, where again the adversary can now make T queries to the function, and it's required to find collisions. Okay. So if you think of this, can you think of an attack? Like there is a very trivial attack that exists here. You have to find collisions. So you can just like you pre-compute to find, because you're looking at the entire table in the offline phase, right? So you just look at find two collisions, you store it in your advice, and then in the online phase you can easily win. Yes, that's why we need the ID. So that's why we need to, initially I had told you, right, ID can be a fixed value or depending on the system. But now we specifically want ID to be random. Okay? So what happens is in the offline phase, the adversary it can still see the entire function, but now the function it's just not a function, it is a family of functions. Okay? It sees the family of functions, it stores S bits, but then in the online phase, it gets a challenge solved. So this challenge ID. It gets the challenge ID, and now it has to make queries, it gets to make query to the function, and now there is a restriction, then that the output that you find, that the two messages that you find have to collide with that ID. So your output, like this h of ax should be equal to h of ax prime.
So if all the queries the same A will be.
You can make queries with other A, but that's not going to help. So you can also like think of this as domain extension, but when you are given the challenge, your challenge restricts your domain, and you have to like win on that that one particular domain that you're given.
So other than needing the ID, another workaround for allowing advice could have been to restrict the advice to be much smaller than twice the length of the input. Could that also have been okay definitionally at least?
No.
It's some security. Can give some prefix of the.
Some prefix, yeah.
So it reduces the level of security.
Right.
So you'd like to, I think here it's more about the actual concrete
That's family.
Can you say that again? So you're saying you reduce the advice by half.
So you don't allow the advice to be as large as twice two inputs.
So your advice is smaller than 2 log n?
Yeah.
That, okay. Yeah, then yeah, you cannot store the collision.
Right. So,
Yeah.
Sure.
But yeah, that can be, that's true for even when you did not have like in that case when your advice is smaller than 2 log n, then you can't even win with like in the unsorted hash functions. In that model as well you can't. So
here the motivation is to have arbitrary polynomial size.
yeah, so when I'm like talking about this tilde, this is ignoring all the polylog factors. So in this model, the best attack, there is like a trivial attack. So you can think of like this S bit stores collisions, like order of S pairs of collisions. So either the challenge that you get is one of those for which you store the collisions, or you find with the Berkeley attack you find the collision. And Dodis et al. They showed that that was the optimal attack here. So they showed like the bound is actually S plus T square over N. So that is like, so that's the optimal security that a hash function should give, right? And now when we like, so Corretti et al. Next studied the Merkle-Damgård construction. And here, so again, like the adversary gets unbounded access to the compression function, not the bigger MDH function, the compression function. It gets to output advice on that function. Then in the online phase, it gets a sort. It gets to make queries to the compression function, and it has to find collision on the bigger MDH function. And for this, Corretti et al. Were able to show a better attack that like beats the optimal bound. So like basically they were able to show that Merkle-Damgård does not give the optimal security. Whereas in the random oracle model, if you remember, we thought, okay, like Merkle-Damgård is a good enough construction because it was achieving the optimal security. But now they were able to give a much better attack. So
How much better?
so their attack is ST square over N.
Times.
Yeah, S times T. So it's a beautiful attack. So I'll describe the attack. If there are any questions, feel free to ask. So what you do, so first in the offline phase, you pick S random solves, order of S random solves, and for all these solves, you iteratively apply the compression function with 0 messages. So basically what you do is you compute h of a10, whatever output you get, on that you apply h along with 0 message, like the output and the 0 message, and you iteratively do that t over 2 times. Okay. And so like this, for each of these you would obtain a1 prime, a2 prime and as prime. And for all of these, you store a collision. So now your advice would contain these a1 prime, a2 prime and so on, and the corresponding x1 and x1 prime that give collision on the sort. So you make these trails, and whatever you get at the as the output sort, on that you find collision, and you store that as your advice.
But for all of these as IVs, everything that
Yeah, exactly. So now when in the online phase, the adversary gets the sort, it again applies this function with 0 messages iteratively. So you would apply like h a0, then say you got the output a prime, on that you will do h a prime 0, and you will iteratively apply that t times. Now if you analyze this attack, if in the first t over 2 queries, in the first t over 2 times, if the adversary hits any of these salts that were like found in the trails in the offline phase, then it will win, right? It will be able to reach this a prime salt, then from the advice it knows the collisions on these. So the advantage here is order of ST, these are like order of ST, and you get in the first t over 2 times, if you hit any of them, you win. So your advantage is order of ST square over N. Instead of like the S plus T square over N. So definitely like this shows that Merkle-Damgård is not good enough to be used because it's not achieving the optimal security. But there's one thing to notice here. The attack is finding collisions that are order of T blocks long. right? Because what were your collisions here? Your collisions would be all the 0 messages along with that x2, x2 prime. Say if it hit this sort here, and at the end it was like a2 prime, so your collisions would be all these zeros, and then your x2, and the other message would be zeros concatenated with that x2 prime, right? So this is this could be like potentially t blocks long, right? And what that means, so say you have a SHA-2 function where n is 2 to the 256, m is 2 to the 512, and now you are allowing the adversary to have 2 to the 70 bits of advice. Not 70 bits, 2 to the 70 bits, which is already like very large memory. And then this st square over n bound implies that the adversary would have to make 2 to the 93 queries in order to win with constant probability. And so the collision that it will find would be 2 to the 93 blocks long, because we were finding the order of t block long collisions, right? But say, and this colliding messages would be like iota bytes long. 2 to the 93 is iota bytes long. Like you have these picobytes.
I don't know how much is your
At some point I looked at it, now I don't remember. So yeah, but it doesn't make any sense. So no application you give such long collisions. It doesn't, yeah. So we wanted to say we want to restrict the Merkle-Damgård to only hash messages that are up to 2 to the 20 blocks long. So then your collisions would have to be like 2 to the 20 blocks long, right? And so basically you say the adversary wins only if it outputs 2 to the 20 block long collisions. For such an adversary, the best attack that we could find required 2 to the 166 queries. Which is like, which when you compare to like 2 to the 93, this is a lot more queries. And so basically the best attack we found was required order of S, that was like the advantage was STB over N, where S is the size of the advice, T is the number of queries, and B is the how long your collisions can be, instead of ST square over N. And we conjectured that actually this is the optimal bound. This is the best attack. This is the optimal attack, and the matching bound is also like STB over N. So what this would mean is, if SB is smaller than T, then Merkle-Damgård is still achieving the optimal security. So we can still use Merkle-Damgård in scenarios where we can ensure that SB is smaller than T, or basically we can say that B is smaller than T over S. Then we can still use Merkle-Damgård. So, but we were not able to show this bound. We conjectured it, but we were able to show this bound only for a restricted class of pre-computing adversaries. We were able to though show it for B equals to 2. For B equals to 2, we were able to show that any pre-computing adversary, the best advantage it can get is ST plus T square over N. There was a follow-up work by Ghoshal et al., which was able to show our conjectured bound of STB over N for constant B. So they got this bound where they had a factor of like log square S to the power B. So whenever B is a constant, this would be just a polylog term, and this would be like ST over N. So for such a for constant B, they were able to show that yes, STB over N is the maximum advantage you can get. Then in our follow-up work, we were able to give this complicated bound, which I'll unfold for you. What this bound means is when ST square over N is less than or equal to 1, our bound is STB over N plus T square over N. So this is the conjectured bound from our ACDW paper. And again, here we can say that whenever SB is smaller than T, we can use Merkle-Damgård because it's achieving the optimal security. And whenever ST square is greater than N, our bound is STB over N times ST square over N plus T square over N. So now whenever S square B is less than T, then you can use Merkle-Damgård because it is achieving optimal security. So basically, like everything is not lost. You can use Merkle-Damgård only in restricted parameter ranges if you want to achieve optimal like security with it. Any questions?
Yeah, so just to clarify, what is, so I think I missed this before, what is optimal security?
So, so in
The big RAM or
when, so like this, when you had this hash function, like this, you thought of the hash function as a random function, and this was how you model it, like, and then the advantage we showed was S plus T square over N. So optimal security is S plus T square over N.
we didn't have the Merkle-Damgård structure.
So if you think about it, like Merkle-Damgård, when we use that construction, we're getting some additional information, right? We're getting that construction, we know something about it. So basically it's showing that you can use that, so correctly show that you can use that information to do better attacks.
So I didn't get the difference in the two models.
Okay. Yeah. So the first model is where you think of the hash function as a random function. You just think it's like it's idle. It's a random function. Another model is where you think, so you remember in the Merkle-Damgård construction we used just a compression function. Now we still think that this compression function is perfect. It's a random function. But we know some information about this entire construction because we know how it's using this compression function to get the output.
Okay, so
And now you model this as a function, like you model this as a random function, but in the adversary is required to find collisions in MDH, not just H.
in the second model, adversary has access to the small h function.
Yes.
In the first model, adversary has
The
access
entire
to the
function. So basically,
capital
yeah.
H. But if I am given capital H, can't I simulate small h? I just give small messages.
No, there is no small. So the one model is that it's actually a truly random function, so it's a much more complex one.
You just think there is like this function, hash function is like it's a random function, like it's outputting something random every.
Oh, okay.
There's nothing known about this. It's just an oracle that's returning you random values. In the second one, you know the structure.
So the first one was not about Merkle.
It's a best you could hope for.
So on a very high level, I want to compare the techniques. And so the Kuretti et al. Work, where they were like looking at unbounded collisions, they reduced it to a model called bit fixing model, and I'll explain what that model is. So in this model, again, you can think of the adversary in this model works in two stages. In the first stage, it gets to fix some points in the compression function. So say it fixes on on 1, input 1, input 2, input 3 and all, it can fix whatever value it wants. So basically, now H is fixed on those points. Okay. And then in the online phase, the adversary has to find collision for this function that so now this H, the H that's under, like the compression function that's under the attack, is restricted to these P points, that it has to respect the P points that the adversary fixed in the offline stage. Okay. And it's random on all the other points. So except for these P points, it's random on all the other points. So again, like here what will happen is, in the offline case it's fixing these P points. In the online case it will get a challenge solved and it will get to make T queries to this compression function which respects the P points that the adversary had fixed and it is required to find a solution. And Kuretti et al. Showed that if this P equals to ST, where so S was in the pre-computation model, S was the size of the advice, T was the number of queries, and then in the bit fixing model, if P equals to ST and the adversary gets to make T queries, and the advantage is delta, then this implies in the pre-computation model where there is S bit advice and T queries made, the advantage is order of delta. So they gave this reduction. So overall the technique was they gave this reduction to this bit fixing model. In the bit fixing model they showed the advantage was ST square over N. So their advantage in the pre-computation model was order of ST square over N. We in our 2020 paper showed that this bit fixing model is too strong and for bounded length collisions you can get like no better bounds. So it's not good enough, like it's too strong. So basically we showed like even for like 2 block collision finding in the bit fixing model you can achieve ST square over N.
Go back to the previous one. What is the result? So you're trying to prove that the pre-computation model is hard to find.
Yeah, so the bound is ST square over N. We want to show that. So the Kuretti et al. They gave a reduction to this bit fixing model.
So when you say what did they show? They showed.
They like reduced the bit fixing problem to this pre-sampling model. Pre-sampling is basically pre-computation.
So I'm just trying to understand which way the direction was. So
okay. I might have like confused you. 1 second. So if you have like a bit fixing adversary, you can use that. So if you have a pre-sampling adversary, you can use that to break the bit fixing. You can use.
And then they showed also that there is no adversary for the bit fixing model.
Yes, they showed there is no adversary that can achieve better than ST square over N.
Okay. So and what is the next thing you said?
So we showed that the best bound you can get in the bit fixing model for fixed length collisions, like bounded length collisions.
Oh, so the earlier one was not a good one.
No, it was for unbounded.
Okay, that's a difference. So now for bounded length, you're saying that reduction doesn't work.
Yes, the reduction still works, but because it's too loose, so basically the best you can still get is ST square over N. So even for like in the bit fixing model, if I have so basically we could give an adversary in the bit fixing model that achieves ST square over N bound, like at least ST square over N advantage, even for 2 block collision factors. So we reduced it to another topic. We reduced it to the multi-instance model, which is this. Now there is no offline phase, there is only an online phase where the adversary gets instances of the problem. So what will happen is it will get 1 sort, it will be allowed to make T queries to the compression function and it will have to find collision on this sort. And then it gets another sort and this is repeated S times. And in order to win, this adversary has to win in every instance. So it's getting S challenges and it has to win on all S challenges, on all S challenge solves. So it has to find collision on all solves in order to win. And we showed that if the advantage in the multi-instance model, where you're getting S instances and in every instance you're getting T queries, if the advantage is can be bounded by delta to the S, then the advantage in the pre-computation model is 2 times delta. So again, we gave a reduction. We gave this reduction, and then in the multi-instance model, we showed for 2-block collision finding, the advantage is at most st plus t square over n to the power s. So basically, you can think of this part as delta, and so that would imply the bound in the pre-computation model is 2 times delta, which is st plus t square over n. So the follow-up work of Ghoshal et al., they used the same model. They used an observation that finding large collisions is very hard. Like finding, so say like log n sized collisions, like log n inputs going to the same output under the compression function is very hard. In our 2022 paper, we still reduced to the multi-instance model, but how we analyzed it was a bit different. So say xi is the indicator that you succeed on the ith instance. So in the ACTW20 paper, we were trying to bound this probability that you win on all challenges, x1 to xs. In the here we were trying to show that this we bounded this to delta to the s, and in the AGL 2022 paper, instead we analyzed this probability that you win on the ith instance, given that you won on the previous I-1 instances, and so here we are required to only bound this to delta. Okay. And here, so what you can do is you can, so how we analyzed here, so there is a reason why we could do better in this, when we are looking at the model in this way. That is because here we had to use compression, because we have adaptive adversaries, and also there is a technique called compression based proofs. We had to use that, and there sometimes they are like very unintuitive, and so if you know compression based proofs, you does anyone know compression based proofs? Yeah, okay. I think I'll skip it then. So, if anybody is interested, you can ask me offline.
In the spirit of information complexity?
Yes. So basically, because this is a random function, you should not be able to compress it. But now we know that there are collisions and all. So using such an adversary, we'll be able to compress the random function. But you should not be able to compress it beyond, like it should be incompressible, right? Because it's a random function. So that gives you the bounds. So, and in the right, like on this, when we are trying to bound this to 20, we're trying to bound this to delta. Here, there is only some particular types of structures or particular types of collisions in the previous instances that can help, and we can always bound those, and we don't need to use compression here. Compression can get like very unintuitive, and it's very hard at times to find the compression, like where you are showing the compression stuff. So anyways, so basically what I want to say is you can view this as so in the ith instance you have some at most ST queries you've made, then you get this challenge, and then you get to make T queries, and you have to bound this to delta. This is our objective. And if you look at it, it is very similar to the bit fixing model. What was happening there? You had an offline phase where you got to fix ST points, and then you got the challenge, and you got to make T queries, and you had to find the collision. And there Corretti et al. Had shown if the advantage in this is delta, then pre-computing is order of delta. Now what we are trying to say is, again, like we are again saying at most ST queries are made. You get the challenge and you get to make T queries, and again you're trying to bound this to delta. So these are two very similar things. So why we could get better?
So there's one more part to this, right? Like in the correct tutorial, we also show some bound, the side bound on the fixing it. Now you let do it on your instance version. Right? So does that get more difficult, or is it something you can do? Showing that this kind of
Yeah, we can do better. We can do better analysis because they are doing worst case analysis. There you're allowing the adversary to fix the points. Here you're saying it's a random function, so it's getting random outputs, and those have to have certain structures. Here the adversary can make sure those structures are there. So it can say like, so say one of the collisions I want is, so say I want this kind of structure in the previous queries. So when I'm doing this, as an adversary I get to fix these ST points, there can be ST over two such structures, right? Whereas when I'm talking about a random function, there cannot be ST over two such structures. We can show that with good probability there will be only S such structures. So basically the difference between the two models is here there is this worst case analysis that's implicit. There we are able, in that model we are able to do the average case analysis, which allows us to get better deltas. So so these deltas are actually different.
and this conditioning on various things having worked, does it complicate things?
No, it doesn't affect, because the thing is, these AI that you get, you can say with good probability it has no, you've not queried on that AI. So basically you've not been able to guess a future instance. What would be a future challenge? So that's why you've not been able to like use that. So it doesn't affect that much. So yeah, that's just the high level idea that I wanted to share. And there are some interesting open problems. So again, like getting these time space trade-offs for sponge construction. There is another very popular construction, that's the sponge construction. So there are some preliminary results which show that sponge is no better than Merkle-Damgård. We don't know if it's worse or not. It could be worse as well. And which is not a good thing, because NIST said like let's move from MD to sponge, and there is this model where sponge could, so we can show that sponge is worse than Merkle-Damgård when B equals to 1 and B equals to 2. And for the rest, we think it is at least as bad as Merkle-Damgård, if not worse. So getting that for sponge. So the issue with sponge is, if you know the sponge construction, they use permutations. So there the adversary can make inverse queries as well. So like how I was saying that there is a probability involved. Now with inverse queries, you can ensure some bad events can, like bad things can, the adversary can make sure those bad things happen with inverse queries. And another thing is just analyzing all this in the quantum setting. So in the quantum setting, we even don't know what is the optimal security yet. So analyzing the time-space trade-offs in the quantum setting is
It's not space, really, qubits.
yeah,
You
yeah.
also have
Yeah. Yeah, so that's all. Thank you for
Any more questions? Any questions from the online?
you can go ahead and ask.
Yes, so I was wondering, so here you assumed the small h function is a random function. So I guess people also look at proving securities for small h, right?
The thing is, when you don't think of, so you're saying we don't want to consider small h as a random function. We instead think of it can be any function.
Not any, I mean whatever is the function in use, this whatever standard implementation.
Standard, okay. The thing is, you don't know how difficult it is, right? In the like, so again, as I said before, it's a P versus NP problem. When you have two, someone says, yeah, like these are like the collisions, you can easily verify.
Right.
But finding itself, you don't know how hard it will be in a function. So for a random function, we know, like unconditionally, we know that you need to make like square root n if n is the output like range. So that's why, like, I don't know, like, unless you make certain restrictions on functions, like,
No, you prove security under some assumptions, right?
So
P not
in this symmetry curves and everything, these are not based on just their assumptions, like say disregard. So there are hash functions which are secure under those kind of assumptions. But what gets used in these constructions are some handcrafted
like
functions.
AES. I mean,
In that spirit, yeah.
yeah.
So there is no, I mean they're fast, but hopefully
You just hope they are like, yeah, they're good enough.
so
But yeah, that is an issue in the finals.
so you're saying the other ones which are based on these
They're much slower.
slower.
Yeah, nobody would use it unless we can show these.
Okay. That's not an issue with RSA versus AES.
Say in RSA brings new functionality, like a public key. So it's used only for that. So you do this hybrid functionality. RSA is used only to establish this function when you're using keys.
And AES on its own cannot be a hash function because it's not
I
compressive.
think it's just roughly AES in the spirit of practical constructions. So response means like sharply response. Do they use the same compression functions as, do they have a compression function inside?
No, they have permutations and they truncate down. In the end, you whatever permutation, like, so you basically just truncate it. So the output is still like in say order n, like set n, but the function is when you think of it in the ideal model, random permutation. So yeah, we analyze it in the RPM.
Okay. Thanks for the talk.